So welcome to chapter 3. So in this chapter we'll talk about acids and bases. So in lecture 1, we'll be discussing Bronsted-Lowry theory of acids and bases, and then we'll discuss the flow of electron density in terms of using curved arrow notation and how to show how electrons flow, and we'll talk about the acidity, and we'll talk about two perspectives, quantitative and qualitative perspectives. So let's go into the chapter. So before you go into the chapter, try to review these topics from chapter 2, identifying formal charges from chapter 1, and drawing and interpreting bond line structures from chapter 2, identifying lone pairs from chapter 2, and drawing resonance structures from chapter 2. So try these parts and try to make sure that you have some idea of these topics so that it will be useful and it will help you in understanding this particular chapter. Now let's talk about Bronsted-Lowry theory. So the Bronsted-Lowry theory of acids and bases basically says it's a process of proton transfer. So the entire process relies on proton transfer. So the acids are materials that donate the proton and bases are the ones that accept the proton. So acids are proton donors and bases are proton acceptors. So if you remember from general chemistry, we talked about this before as well. So the acid here is the proton donor, so it donates its proton to the base, here it's water, and releases it to form an anion and the conjugate acid. So the acid creates a conjugate base and the base creates a conjugate acid. So remember this topic of conjugate acid base pairs. Now, so what is the definition of a conjugate acid? So a conjugate acid generally relies from when the base accepts a proton. So a conjugate base results when an acid gives up a proton. So a conjugate base is the acid that has given up the proton. A conjugate acid is the one that accepted a base that accepted the proton. So when you try labeling these. So here notice that, let's try labeling the following example here. Notice the compounds that we have here. So focus on the first two, which are the reactants. Here we want to know where is the proton going from. So look at the compound and look at its conjugate base. So here if you look at it, it has accepted a proton, so which means this is a proton acceptor. And this here is the one that donates, obviously. So we know that the proton acceptor is the base and the proton donor is the acid. So the acidic one becomes the conjugate base. So after it donates the proton, it becomes a conjugate base. The one that accepts the proton becomes a conjugate acid. So this is the idea behind the topic of conjugate acid and base. Now, so let's talk about how to draw these reactions and how to show electron movements. So the making and breaking of bonds involves electron movement. So we use curved arrows to describe the flow of electron density. So here one way of looking at this is the electron density always goes from the base, which has a pair of electrons attacking the proton, and the proton donates its electrons back into the base and leaves it, so resulting in B bond H, where the base bonds with the proton and the acidic anion leaves out. So these are the same curved arrows that you used in drawing resonance structures, but here we are trying to show the actual describing of the physical movement of the electrons. So here we are actually showing how the actual movement of electrons is going from. So learning to draw these mechanisms is one of the most valuable skills in this class. So once you know how to draw these mechanisms, you will be able to draw any general organic chemical mechanism and understand how the mechanism generally works. So let's take the example here. So always remember, base attacks the proton on the acid and the proton donates its electrons back to the anionic substance that is present just before it, and the resultant gives a conjugate acid and whatever is left becomes the conjugate base. So always remember, the base attacks the acid using a pair of electrons and the acid cannot lose its proton without the base taking it. So all acid-base reactions generally occur in one step. So you cannot have multi-step synthesis. So this is just happening in one step. So the mechanism shows two arrows indicating that there are two electron movements simultaneously. Notice that this electron movement 1 is, then this electron pair is the second movement. So this is the one that forms the bond. So this part forms the bond and this part breaks the bond. So that's the difference between the two pairs. So one breaks it, one forms the bond. So let's talk about a multi-step reaction mechanism. So here we have shown there is a showing of a multi-step reaction mechanism. So they are asking you which steps below are the proton transfer. So remember that proton transfer only occurs when a lone pair of electrons attacks a proton. So number 1 here, so this is a proton attack, and number 2 you have, so notice that here it is breaking the bond, so this one is not a proton attack, and again here also there is a breakage of the bond, so this is also not a proton attack, and here notice that there is a lone pair that is attacking a proton, so this is a proton attack, so there are two of them. So here there are two of them. So once you remember this, how to draw the mechanisms, it will be making it easier for understanding how mechanisms can be drawn. So once you're familiar with how to draw the arrows and where every one of them goes, so just learn the first one, which is the concept of proton attack. So this process is called proton attack or proton transfer. So these are the two names that we commonly use. So proton transfer is the most commonly used name, but you can also use the term proton attack. Next, let's talk about how to quantify acidity. If you remember from general chemistry, we used to name how do strong acids differ from weak acids and weak bases. So the strength of the acid or a base is generally helpful to predict how the reactions will progress. So we'll learn two things. One, we'll learn quantitative strength analysis using the value of pKa to compare the strength of the acids, and we'll also do qualitative strength analysis comparing the general stability of the structure. So the two things, one by using number of the actual number pKa, and second by using the structure itself. So let's start with quantifying acidity. So what is pKa? So let's talk about pKa. If you take an acid, the whole purpose of the acid here is it's a proton donor, which means there is a base. For example, let's consider the base to be water, and let's say the base has two electron pairs. So this one attacks the proton. So notice that here we have H dash A, and here this electron pair goes put to A. So this results in a formation of A minus. The reason it gets minus is because it gets an extra electron pair. Plus O H H H. Notice that the electron pair that it's using, so it forms the bond using that electron pair, which means that there is only one lone pair left, and because it has lost one electron pair, so it gets a positive charge. Now, so notice that this is the acid, the base, and this is the conjugate base, and this is the conjugate acid. So this process is called dissociation. So dissociation is the process where the protons are removed from the acid. So now how many do they occur? How many of them occur? So this is the question that we want. How many dissociation? For example, let's say if there are 100 molecules in total, how many will actually dissociate to form a conjugate base? So this, understanding this, is what we talked about in general chemistry. If you remember, in general chemistry we talked about a strong acid and a weak acid. A strong acid, there is full dissociation. So if you remember, a strong acid undergoes creates a full dissociation. A weak acid creates partial dissociation. So it creates partial dissociation. So the level of dissociation is used to represent, the value that we use to represent this is called Ka. So Ka is called the acid ionization constant or acid dissociation constant. So acid ionization constant or acid dissociation constant. So where do we get this Ka from? So if you remember the equilibrium constant, so equilibrium constant is the concentration of the product by the concentration of the reactant. So the product here is A minus times H3O plus over HA and H2O. So to find Ka, what we do here is we multiply the equilibrium constant with the concentration of H2O. So that gives you the value. So just push this way. So whatever is left will become your answer. So A minus into H3O plus over HA. So notice that the main values that decide Ka are the value of A minus, H3O plus and HA. So this value is a constant. So Ka is very high for strong acids. Ka is really small for weak acids. Right? So Ka is generally small for weak acids. So if the acid is strong, so one way to know it is, will it be bigger than 1 or smaller than 1? So most acids generally have a larger value. For example, if you take Ka values, generally they range from 10 power negative 50 to 10 power 10. So the size of these numbers is generally very small or very big, and because it's too big, so it's hard to work with. What we do here is, rather than working out with Ka, we take the negative log of Ka. So what does the negative log do is, it removes the power, so it removes the base of the value, so it becomes 10 power negative 50 to 10 power 10 is the value of Ka. So when you do negative logarithms, so it removes the base, so the base 10, so it removes the base. So you will be left with the value negative log Ka. So this negative log Ka is called as pKa. So it's a constant that we use. Now this pKa, when we use negative log, it changes the sign of the power and gives it a whole new values. So the values range from minus 10 to 50. So the values range from minus 10 to 50. So this is how we can determine the Ka. So this pKa values are generally ones that range from minus 10 to 50. So we told that when Ka is high, it's true, they are strong acids. When Ka is low, it's weak acids. But the same thing is true. What happens here is, when Ka is high, pKa is low. When Ka is low, pKa is high. So for strong acids, pKa is low. For weak acids, pKa is high. So if you see a smaller value, it means it's a stronger acid. So the smaller the value, the stronger the acid. The larger the value, the weaker the acid. So this is how pKa can relate to the acidity of quantities. So when you look at, in general, organic acids are generally weak acids. For example, when you take this table here, notice the value for H2SO4. H2SO4 has a pKa value of negative 9. So which means that it's a really strong acid. But notice that the stronger the acid, the conjugate base is the weakest. So this is the opposite way in which it works. So if the acid is stronger, then its conjugate base is weak. So if the acid is strong, then the conjugate base of that acid is generally weak. In the same way, if the acid is weak, then the conjugate base of that acid, so if the acid is weak, then the conjugate base of that acid is generally going to be strong. For example, if you take the acid here at terbutanol, terbutanol is a weak acid with a pKa of 18, but it generally is the strongest base. So this is how we can see. And how to differentiate H2SO4 from other HCl. For example, between HCl, is that when you look at the pKa value for H2SO4 is -9, for HCl is -7, which means that HCl is 100 times stronger than, so sorry, H2SO4 is 100 times stronger than HCl. So if pKa value increases by 1, its power increases by 10 times. So this is how you can know the how to quantify the acidity of any given quantities. Now, so you can also use pKa to compare the strength of the bases, because the stronger the acid, the weaker its conjugate base. So this is one way you can also judge its bases. Now, how to use pKa values to predict the equilibrium? So with the relevant pKa values, you can predict which direction an acid-base equilibrium will favor, whether it favors the product or whether it favors the reactants. So the higher the pKa, the weaker the acid. Remember this idea: lower the pKa, stronger the acid; higher the pKa, weaker the acid. Now let's look at the condition. If you remember from the conditions, if you remember from the common conditions, so if you remember from the Le Chatelier's principle, so we know that the equilibrium always favors the weaker side. So we know that the equilibrium always favors the weaker side. So which one is weaker here? So weaker side is the weaker acid. But how do you know which is the weaker acid? Is always choose the acid and the conjugate acid. So always compare the acid and the conjugate acids and their pKa. So whichever has the higher pKa, that side is weaker. So remember this concept: the higher the pKa, the weaker the acid. So whichever side has the higher pKa, that side, the equilibrium will always be in that side. So the reaction always demonstrates that it's always true in an acid-base reaction, where the equilibrium always favor the weaker side, weaker acid and the weaker base. So here the conjugate acid, so we are comparing, always remember this, we are comparing the acid and the conjugate acid, so on both sides, and we are comparing their pKa's. Whichever has the higher pKa, the equilibrium always favors that side. So whichever side has the higher pKa. So this is one way of knowing where the reaction will go towards. So subtracting this pKa values, if you notice, we have, if you take it from the pKa values, so we can say that 50 minus 15.77 is 34. So which means that it's about 10 power 34 times more products than reactants. So this is how you can compare the pKa value. So the value itself, the difference tells you how many times it's much more favorable to one side. So it's not really much of an equilibrium, but more of an irreversible reaction. So once you cross the barrier of above 10 power 3, then most of the reactions are generally irreversible. So where you cannot reverse the reaction back to its original reactants. So this is one way we can judge the reaction based on the pKa values. So whichever side has higher pKa, the reaction favors that side. Right, so this is the main important point by using pKa values, how to compare the acids, and always compare acid on reactant and conjugate acid on product side. So this is the main rule by which we calculate whether the equilibrium goes from one side or the other side. So next, to determine the relative strength of two acids without knowing their pKa values, we compare the stability of their conjugate bases. So remember this idea, the stability of their conjugate bases. So when do we do this? If we do not know their pKa values. Right? So the stronger the acid, the more stable its conjugate base. So this is the prime point to remember. So the more stable the base, the stronger the acid. So when you have an acid when an acid loses a proton, so it forms the conjugate base. So which generally will have a lone pair of electrons. So that results from the loss of the proton. So to determine the stability of this conjugate base, we are actually looking at the stability of that lone pair. So this is the point that we are going to use to entirely determine the entire sense of qualitative analysis. So what are the things that we use to qualify acidity? So the more effectively a conjugate base can stabilize its negative charge, the stronger the acid. So stabilization generally happens from four main factors that generally affect the stability of a negative charge. The first one is the type of atom that carries the charge, and second is the resonance on that carbon, induction on that carbon, and the type of orbital where the charge resides. So these factors can be remembered by the acronym ERIO. So A represents the atom, R represents the resonance, I represents induction, and O represents the orbital. Now, so let's dig into each one of them. So remember that these are things that you do in order of importance, which means that we always check for the atom that carries. Only when both atoms are the same, then you go to resonance. So you always go from one to the other. So order of importance is ERIO. So this is the order of importance in which side you go towards. So this is the order of importance in which side you go towards. So you start with the atom, and if atoms are the same, then you go towards resonance. If the resonance also gives you the same answer, then go to the induction. If induction also gives you the same answer, finally go to the orbital. Now, so let's start with the atom. Let's consider two structures that are having the proton. So one of them is butane, one of them is propanol. So when you want to compare the acidity between these two structures, we want to know which one, where is the negative charge. So first thing you do is draw its conjugate base. So when you draw it conjugate base, basically remove its proton. So remove the proton and add the electrons back into the compound that's attached to the proton. So that gives you a negative charge on the carbon here. Here on the second structure, so the proton leaves, the charge goes on to the oxygen. So that gives you a negative charge on the oxygen. So we need to draw the first thing is we need to draw the conjugate bases. So once we draw the conjugate bases, next one to determine is which one is the atom that carries the negative charge. So the first rule to remember is larger the atom, the more stable the negative charge. Again, remember this structure, the larger the atom, the more stable the negative charge. Here between these two compounds, here it's carbon that's handling the negative charge and here it's oxygen. So oxygen is larger, so which means that it's generally going to be more stable. Now the problem is you cannot determine the size easily when you are in the same period. So what we do here is, if in the same period, what we add the second condition, if in the same period, because the size difference is not that high, so if in the same period, then choose the element, so choose the atom with higher electronegativity. Remember this again. So when you are choosing between two atoms, so if they are also in the same period, don't choose the size as the factor, because size might not represent, the size difference is really small. If you are in between two different periods, for example, if you are comparing between oxygen and sulfur, then you would choose sulfur because sulfur is larger. But when you are comparing between carbon and oxygen, notice that both of them are in the same period, in period 2, which means that we need a little larger, another basis for justifying which one to put it on. So if they are in the same period, choose the atom with the higher electronegativity. So between carbon and oxygen, so oxygen has higher electronegativity, so which means that it's generally going to be more stable. So it's generally going to be more stable. So this is how you can determine based on the atom. So remember, the first thing to remember is take the quantity, write its conjugate base, and check the atom with the negative charge. Check the atom with the negative charge, then follow these rules. So now, because between these two atoms this is more stable, So which means its acid, the original acid, is generally going to be more acidic. So this is how we determine the acidity of any given atom without having to even have any pKa values. You can judge this by many methods, so you can prove this based on the methods that we have. Next is resonance. So we know that resonance also stabilizes the negative charge by delocalizing it. So this process, so how do you compare it between the two acids? For example, we have ethanol and acetic acid. So the first thing we want to do is draw the conjugate base, which means that the proton leaves the electron pair will go on oxygen. Here also again the proton leaves, the electron pair will go on to the oxygen. Now draw the structures that are left. So you have oxygen with 6 lone pairs and a negative charge, and here you have a double bonded oxygen with 2 lone pairs and oxygen with 3 lone pairs and a negative charge. Now between these two compounds, which one is the most stable? Now when you look at this does not have resonance. Which means the charge here is localized. So more delocalized it is, the more stable it is. If you look at the second structure, if you look at this structure, so notice that this electron pair now, notice that this can go, so lone pair to the bond to lone pair. So remember the first one, allylic carbocation. So this is the carbocation, and so the allylic lone pair. So this is an allylic lone pair. So which means that now it can move. So which can cause a resonance structure where it can create bond oxygen and double bond oxygen. So these are the two resonance structures that this compound has. So because it has delocalized, so because the charge is delocalized, it's generally going to be more stable. So whichever has more delocalization and whichever has more resonance, that generally ends up having the acidity. So the more stable it is, the more acidic the compound. So here acetic acid is more stable, more acidic than acetic ethanol. Next, let's come to the topic on induction. So induction can also stabilize the formal negative charge by spreading it out. What is the induction here? So what is the difference between induction and resonance? So induction is the phenomenon of having to have more atoms that are trying to push the electron, more binding a. So induction is the process where you have more electron withdrawing atoms that are going to withdraw the electron density from their surroundings. So thus stabilizing the negative charge. For example, if you take acetic acid, in acetic acid there is no electron withdrawing atoms, but when you compare it with trichloroacetic acid, notice that there are chlorine atoms. Chlorine atoms have heavy electron density. So because of their heavy electron density, they will try to push their electrons towards the chlorine. So the electrons will try to be pushed towards the chlorine. This causes the charge delocalization. So this causes charge delocalization, and because of heavy amount of charge that is present there, this causes the entire structure to become more stable. So when you have electron withdrawing atoms, on the beta carbon. So what does that beta carbon mean? So remember the negative charge and how the structure undergoes. So let me draw the conjugate base for this. So this is the conjugate base, and we have oxygen on here, and there is chlorines here. So the negative, so oxygen is bonded to a carbon. This carbon is called as the alpha carbon, and that alpha carbon, the adjacent carbon after that is called the beta carbon. So if the beta carbon contains, let me write it as a short form, electron withdrawing groups. Electron withdrawing groups are any large structures with high amount of negative charge towards them. For example, chlorine, fluorine can be considered examples of electron withdrawing groups, right? If it contains electron donating groups, or electron deficient groups, for example, aluminum, boron, etc. are generally examples of electron deficient groups. then so this causes more stability, this causes less stability. So that's the difference between the structures. So whichever has more delocalization or more electron withdrawing groups on the beta carbon, that generally has more acidity. So that's why the second structure is more acidic in comparison to the first structure. So as you add on more and more chlorines, notice the change in the pKa value. So the pKa value reduces to a very high extent. So the more the electron withdrawing groups on the beta carbon, so the more stable the conjugate base. So and the closer the electron withdrawing groups to the negative charge, the more stable the conjugate base. So these are the two things that we can consider for the structure, the concept of induction. Next, let's talk about orbital. So the last one is the type of orbital can also affect the stability of the formal negative charge. So here, the closer electrons are held to the nucleus, the more stable they are, which means the shorter the atomic orbital, the closer they are to the nucleus. The closer they are to the nucleus, the more stable they are. Now, between the three main structures that we know, the three main orbitals, one is sp3 orbital, sp2 orbital, sp orbital. Sp orbital is the shortest one. So because it's the shortest one, it means it's the closest. Because it's the closest, it's the most stable. So the closer it is, the more stability that it gets. So this is how you can use orbitals to quantify. So here, if the negative charge is on the sp orbital, so it's generally going to be more stable. The second stability goes to sp2 and the last one is sp. So sp gets the least stability because it's farthest from the nucleus. So consider there are two structures here. Consider the two protons here. So here is one proton and here is the other proton. So when you draw its conjugate base, let's say we try to remove both the protons. So this results in the electron pair going there. Now let's try the structure now. So these are the two structures that you end up with. Here the negative charge is on the double bond, here the negative charge is on the triple bond. So the larger the bond, the more stable it is. So triple bonds get more stability over double bonds. So here carbon ions are generally more stable when they have sp orbital than sp2 orbital. So the lone pair here is on sp2, here the lone pair is on sp. So because sp is more stable, so that generally ends up going more acidic, and it always ends up losing this proton than this proton. So the likelihood of this proton losing is more higher than the likelihood of losing the other proton. So this is how we can use orbital as a way to justify stability or to justify the stability of the compound. Next, so let's try between these three and let's try to compare this. Notice the pKa values of the compounds with the same number of carbons but different hybridizations. Ethane has sp3 hybridization and has the least acidity. Ethylene has sp hybridization but has moderate acidity, but acetylene has higher acidity in comparison to both the others because of the presence of the sp orbital. So this is how, when assessing the acidity of the protons, we generally use this method of ARIO in order of importance of these stabilizing effects. Now we are going to come back to this over and over again in other chapters as well. So if you are familiar with the topic of how to differentiate or how to know which one is more acidic, so just use the principle of ARIO: atom, resonance, induction and orbital. So it is typically helpful to use this order of priority. So because when comparing the stability, because it isn't 100% reliable, but you can get exceptions. So ethanol in general, when you look at ethanol and propylene, ethanol is generally more acidic than propylene. So therefore the conjugate base of ethanol generally must be more stable. But if you look at the actual structure, you end up with a localized charge here and a delocalized charge here, which means that the propylene's the charge here generally has a resonance stabilization. But in order of a priority, if you look at it, it's generally accurate, because when you look at the order of priority, here the atom that holds the negative charge is carbon, here the atom that holds the negative charge is oxygen. So that's why give the order, order of priority importance rather than the individual parts of the order. So it can be resonance stabilized, but provided it does not have to, so it has to follow the order. So it has to be atom stabilized on the right atom, only then it can be. So when you have a tie in the atom structures, only then you can go to the resonance. So this is how we can use order of priority as a way to justify the acidity of any given substance. So ARIO is also only a guideline of priority, so it sometimes fails. For example, we know that equilibrium lies to the right because we know pKa values. So for example, when you take a pKa value between acetylene and ammonia, we generally judge that whichever is the weaker side. So notice that ammonia is the weaker side. We judge that the equilibrium will lie to the right. So if we had judged the conjugate base stability, we would have concluded that the negative charge is on nitrogen, which is more stable than carbon. So that can be predicted, and we would have been wrong. The reason is because for some acids, we simply need to know the pKa values because there are exceptions to the ARIO priority. But most of the examples that you're going to do in this chapter are going to end up not being those exceptions. We are going to have proper structures, and that will end up having a proper priority. So just use that framework to work with. So try to use this example, and here they are asking about difference between the two protons, and they are asking you predict which proton is more acidic in each of these compounds. Now let me do the first one. If you look at the first one, if this proton leaves and it gets a negative charge on this carbon, the negative charge is on the carbon, and if this proton leaves, the negative charge is in the oxygen. So if you remember the ARIO priority, so we talked about atom. So atom, here it is between carbon and oxygen. So where carbon has negative charge and oxygen has negative charge. Now which one is more stable? So we know that they are in the same period, so we'll have to evaluate using the electronegativity, which means that we know the oxygen has electronegativity, higher electronegativity. So which proton is more stable then? So the more stable proton is the red one. So the more stable proton here is the red one. So we can write based on the structure that we have. So try the other two examples and see if you can figure out whether we can justify the stability of each proton in each of these compounds. So try the following, try these two examples. So pause the video right here and try these two examples. So let's try this problem. So I'll be solving this and I'll be giving you some more examples. So let's try this problem here. So in this structure, notice that there are two protons again, red and blue, and they are asking us to compare which one is going to be more stable. So use each proton and try to draw its first conjugate base first. So you have So let's draw the red ones first. So the red ones first, when it goes, the red one goes, you get 2 electrons on the nitrogen, you get a negative charge. Now, so you have NH, that's gonna stay the same way. So let me draw the other ones. So this lone pair will stay the same, so H will come here, but here, so we are going to lose this electron in this one. So this proton will go here, and this proton here. So these are the conjugate bases that we end up with. Now between these two structures, we want to know which one is more stable. So remember the order or rules first. So the rules are ARIO. So the first one is the atom. Notice that on negative charge here between the both structures is on nitrogen, so it's gone. The second one is resonance stabilization. So look for the resonance structures here. Is there any allyl? So remember the concept of resonance and the criteria that resonance needs. So resonance needs here, is it adjacent to a carbon? So notice that there is no allylic position here, so there is no chance of having a resonance. So there is no resonance in this structure. So if you want to know why there is no resonance, just review chapter 2 on how to draw the resonance structures, where I explained much more clearly. And if you remember it, it makes it easier to understand this. Now notice that here it is an allylic position and there is a lone pair here. So notice that this is the vinylic position and this is the allylic position. So nitrogen is in the allylic position. So this results in an allylic lone pair. So what happens when you have an allylic lone pair? So this results in the two lone pairs, so the two pair of electrons going to the bond to lone pair again. So that results in a resonance structure where you end up with nitrogen with one lone pair, and you have oxygen with three lone pairs of electrons with a negative charge. Now this here is the resonance structures between these two compounds. So because it has resonance, so the nitrogen has resonance, which means that the charge is delocalized. So when the charge is delocalized, it means it's more stable. So which means that this proton is more acidic. So the blue proton here is going to be more acidic. So now try other problem. So in these structures, so try to do one by one. Always remember, first draw the conjugate base, only then try to judge its judge basing ARIO. Right. So also try the other ones. So also try this one. So notice that in this, if for your hint I can show you one. So one way of noting here is that notice that both of them are on oxygen, so A will not match. So you are going to go towards resonance. So resonance will come here for this structure. So notice that there is induction on this structure. So which one are you going to choose? So remember the order of importance, always give resonance first, which means that this is going to end up in a resonance stabilization. So if you are done with that, so try these 6 problems. So with these 6 problems, you will be able to understand the entire topic of how to draw, how to judge a given compound's acidity based on its proton. So remember the idea behind this. So once you are familiar with this, it makes it easier. So with that, we are lecture 1.